Good morning, everyone. The purpose of this talk is just to do a basic 101 on AI. We'll talk a little bit of the history. I'll show you how simple maths can actually perform one of the neural networks, which is one of the big exciting areas of AI. And then we'll go into a few use cases. So this is supposed to be a light entry into AI. I'm going to try and avoid using any heavy maths or any heavy concepts. So we'll go straight in. I mean, the first question, what is AI? We was touched upon briefly on the keynote speech. The big problem here is, what is intelligence? I mean, how can we define artificial intelligence if we struggle so hard to define what intelligence is? You could spend your whole life, well, philosophers have spent their whole life trying to define what intelligence is. One definition I picked up off the reliable internet is the ability to acquire and apply knowledge and skills. From a software perspective, the way I define AI fits into this one, which is, I suppose, why I picked it. When I was at one of the early neural networks I ever made at university, it was to do facial recognition, to tell the difference. You could give it a picture of a male or female, and it could, with about 80% accuracy, get it right, given that data set. And I think on the same data set, human was about in the high 70s, so it was much the same. But the reason I bring this up is because for me, this is a good way of, from a software perspective, what the difference is. Because the obvious question that followed from that was, well, how does it tell the difference between a male and female? Does it look at the eyes? Does it look at the mouth, the facial structure, all that kind of stuff? The truth of the matter is, I don't know. I genuinely don't know what it does. As a software engineer, what I do is I program it to learn from the data it's given. So I can talk about and tell you how it learned from the data I gave it to, but how it actually tells the difference between a male and female, I don't know. And that's a large chink in the armor for AI, because that holds true across things. We build AI models and AI networks. We know how they're built, but we don't truly grasp or understand the actual functionality of it in terms of how it arrives at decisions. We can break the model down, but at the end of the day, we don't really understand how it arrives at the solutions it does. So for me, as a programmer, I define something AI. If I can't tell you how it knows the difference between a male and female, but I can tell you how it learned. Traditional programming would be the other way around. Traditional programming, you'd say, well, you would look at the eyes or all these kind of heuristics that we might try to use. So I would tell it how to tell the difference. But with AI, we don't. We just tell it how to learn from the data we give it. The other mass confusion, and I hope this is going to try and solve a lot of the terms that we hear when we talk about AI. AI, for me, is the very catch-all term. That's at the top of the tree. So when we talk about AI, that's a very broad field to say. Not limited to these options, and underneath it, we'll probably hear more about machine learning. And then underneath that, which we're going to go into a little bit of detail, artificial neural networks. Other fields such as evolutionary computation, we'll do a little bit around this, and fuzzy logic, and there's a whole host of other ones. But the main point of this slide was to show the slight difference between when we talk about AI, machine learning, and neural networks. This is how they all roughly fit together, and not to be easily confused. So we're just going to dive into a bit on the neural networks part. This slide is this is a very old drawing. I think this is in 1890, I think it was in Spain. And the reason I bring this up, this was the first time that we really figured out that the brain wasn't just a big lump of grey mass. This was the first picture that really showed that we have individual cells, which we've gone on to create neurons. So from that, we'll go into a bit of brief history. So from that picture in 1890, when we figured out there's a bit of a neuron going on here, and it's a bit of mass, it wasn't until the 1940s when we started to figure out what's happening in the neurons, what's actually happening in these cells. From an engineering perspective, on a basic level, we still to this day don't understand every aspect of it, but we grasp the fundamentals of it. Then, moving into the 1950s, we started talking about, well, maybe we can turn these neurons into an artificial system and simulate it using computing power. The first commercial instance came from Madeline, and that was used in America for removing echoes from phone lines. And from what I hear, it's still actually used to today. So again, the point of this slide is to show that AI isn't this new thing a lot of people think it is. A lot of the theory and a lot of, even to today's practical use, actually has its history back into 1940. Moving from 1960s into what's called the dark period, everyone got a bit bored of it by then. It wasn't really doing what we thought it would do. There was also an engineering problem because we could get At the time, we could only do 2 layers of neurons. I'll explain that in a minute, just so bear that in mind. We couldn't replicate. We could replicate all the logic gates that you see in electronics, but we couldn't get to replicate what's called an exclusive OR gate, which was known as the exclusive OR gate problem. And that was a large part of why we sort of took this break in the 1960s, because it wasn't until the 1980s that we could start having multi-layered neural networks and figure out how to train those. So all of a sudden it became more interesting, because now we can start replicating electronic systems a bit easier, because we can do the whole spread of logic gates. A chap called John Hopfield, he developed what's called also at the same time backpropagation came out. And backpropagation was what reignited neural networks, because this is what allowed us to do these deeper neural networks and solve these more complicated problems. But even then, I studied AI in 2001, and it's sort of, even then I knew of it, and it was kind of interesting, kind of cool, to be honest with you. But it still didn't take off then. And my reasoning for that is because I think at the time we had the computing power, but the reason in 2001 why it wasn't really that interesting is because we weren't really getting good results from it. It was kind of right sometimes, but very niche cases. And I think the reason why it's really exploded now and starting to get really traction is because now we have large data. The problem back in the early 2000s for me was that we thought, I don't know, 100, 1,000 samples was quite a lot of data, but that's very narrow to learn and train things from. Now we talk about millions, and this is why we see the much more interesting results that we get, because we have a large data set for these things to learn from. This is, I'm not a biologist, so I'm not going to go into this too much, but the other misconception about AI is that a lot of people seem to think that we're trying to replace humans, or there's this big conspiracy. But the truth of the matter is, AI is a very emotive phrase to use. It's a good marketing phrase to get people interested in a particular tool and a particular method of doing software engineering. What we're really doing, and I think the lot of field is doing, is we're taking inspiration from the natural world. We're looking at how brains work, how the natural world solves its problems, and we're trying to re-engineer that and figure out and use it for our own purposes. So if we look at this neuron, we can see the neuron cell, we see the axon, which is the input, and the dendrites are the outputs. The rest of it, that's more of a biology thing. But what we really look at from a neural network perspective is these inputs, the outputs, the dendrites, and the cell body. And we'll go into that in a second. So how does it work? This was the original perceptron, it was called back in the 40s, I think. And from here, we can see this is more of an engineering model of what we're looking at. We can see the inputs to the cell, which in biological terms are called the axon. The nucleus is where the computation happens, and we'll go into that in a second, and the dendrites being the outputs. So what happens in these cell bodies? Well, the inputs, if we can just attribute a numerical value to them, in this instance I've just chose these at random, we have 1, 0.5, and 0.1. What the cell body does is it adds these numbers together, and in this instance we get 1.6. And what we call an activation limit is when the value of this sum is above 1.5, then the output is a 1. If it's below that, the output is a 0. That's it. That's, well, apart from the next problem, but that's why it's not that hard to comprehend. Now you might ask from here, where's the learning part? How does this learn from this very static situation? Well, what we do is we give each input a weighting. So one input might be more important than the other one. So what we're saying here is the one on the far left here is a weighting value of 0. The one in the middle, 0.5, and the one on the right, 0. We then multiply the input with the weighting, and then we do a similar calculation we did there, and then we add the sum of those together. In this instance, we get 1.25, which is lower than 1.5, so the output is 0. Now what we're doing with learning, when we talk about learning and how training a neural network, all we're doing is we're figuring out the weighting of the inputs. So we can change the weighting of the inputs, and through those calculations, that's why we start to learn. Now, one neuron in itself isn't very interesting. So this is why we talked about layers, which is what I talked about earlier. So we have the output of one neuron acting as the input of the next neuron, and so on and so forth. To put it into perspective, in theory, again, I'm not a biologist, but I've been told that for a normal decision to go through in a human brain, we're talking about 10 layers of neurons that this goes through, rumored. So what we do is we put the inputs first time round, all the weightings are completely random numbers. We've just randomly assigned the weights of the inputs. Complete guess. So obviously the network's going to be completely wrong the first time round, because it's just a complete guess. But what we can do is we have our input, and when we're training it, we know what the expected output is. So again, going back to the example I had earlier, we would have a data set of, say, 1,000 pictures of males and females. Each one of those pictures would be labeled male or female. That's the training set. So we have that input, and I know what output I'm expecting for it. First time round, I'll show it. The neural network will have a guess, be completely wrong, but that error, we can use how far it is wrong to then recalibrate all the weights. So that's what we call pass forward. So we've given it an input, we have an output, we know how wrong it is in this instance, we'll adjust the weights, and then we'll try again. And we keep going through this process over and over and over again until it's correct. In a way, it's sort of like repetitive learning. You sit and read a book over and over and over again until you've learned it. It's the same with neural networks. And a deep learning neural network, all that's happening here is that we have more than 2 or 3 hidden layers. So whenever people talk about neural networks and in deep learning, the reality is that deep learning is there's just more layers involved in the network. It's not anything more fanciful and complicated than that. The thing I'm sort of brushing over, because this is where the complicated maths is, it's not that, some method is the maths that we use to do the calculating from the error what the weights of the inputs should have been. But you remember I mentioned earlier something called backpropagation, and what reignited the neural network field, because it was until backpropagation, we could only calculate the one layer of neurons because we knew what the error that was there, so we can from the error infer what the input should have been. The problem is, if we have the error here, what does that mean for the weights here? We couldn't really have any visibility in calculating what these values should be. Backpropagation came round, and as the name suggests, all we do is we propagate the error back from the weights. So we pass the error back through the thing. The maths isn't that complicated, but I promise to use only adding and multiplying, and there's more than that involved, but you shouldn't really be scared of it. So from here, we'll go to some current use cases, and these are the use cases that I'm aware of and I've talked to people about. The first one I'm going to mention is games. It seems a bit odd, it's unimportant from an engineering perspective, but gaming in computing world is one of the most hardest things you can do from a graphics rendering perspective and the maths perspective. If you look at tic-tac-toe, in the early days, when you're playing tic-tac-toe, there's only so many combinations. So from a programming perspective, if someone does one first move, you can then calculate all the permutations that player is going to go from there, and then play from so you can brute force it. So that was one of the first ones that computers started to beat humans on. Then if we move over to chess, as was mentioned in the previous talk, chess is a bit different, because once you get to 10, or, we see numbers here, after 2 moves, there's 72,000 possible permutations after that point. After 10, we get this number, and then after 13, then you start really getting into arguments with mathematicians on how many possible movements there are. So there's a large number. So all of a sudden, we can't brute force it now. We can't play chess based on calculating all the possible permutations we can go from here. There has to be some strategy. There has to be some thinking about it. And this is where AI started to come in. You can do a bit of blending. The reality is we do a bit of blending in this. There's a bit of brute forcing. There's some intelligence involved in it. So that was why chess was a good moment for AI, but the real moment came with Go. And that's just because we can see the numbers involved here. Again, as mentioned in the keynote, we're talking about the number of particles in the universe after a few moves. You can't brute force that. That has to be pure AI. That's strategy. This is a game purely based on strategy. AI has to be smart and think about what it's doing. Another field that AI does really well with is image processing. One of the good causes of it is it's actually being used to do cancer detection. As I mentioned earlier, if you think about it, what we're doing here is not too dissimilar from the differentiating between a male and female. We're doing pretty much the same thing. We're giving the neural network pictures of non-cancerous pictures and pictures of cancerous pictures. And the neural network learns from that in the exact same way. And it's actually throwing up some very interesting results in the field, and it's getting some real headway into that detecting cancer. The other one, I made this slide a few years ago. This was big at the moment. But the point of this slide as well is that we hear AI being used for all sorts of things, but we shouldn't get too carried away. There are other ways of solving problems without using AI. facial recognition is one. We've been able to do facial recognition using classical computing for quite a while now. The advantage that AI gives over the traditional methods, though, is the traditional method, you'd have to set perfect face on and have a completely engineered situation for you to do the detection. What AI allows us to do is, if the face is slightly different, if it's angled different, maybe they're wearing different glasses, the AI can handle all these differences. It doesn't have to be as pure and as exact on as the engineering one was. So it can handle noise and it can handle imperfections a lot better. Natural language is another one. So we've all used Google Translate. But what I'll do is to break down the problem of, if we call it Amazon Alexa, although this isn't really how Alexa works, but to show how it's not all about AI and these sorts of systems. What could happen here is that we have our home device that just sits and records when it should. We won't go into that one. Records when it should, what you've said, and then takes that MP3, uploads it to the cloud. The cloud then uses AI to convert that MP3 into a text file. That text file is then passed into a normal program because it's just a text file and computers can handle that, or classical program can handle that. Then uses AI for the output to turn its output text into an MP3 player, which is downloaded back into your player, and plays the response that you expected from your smart assistant. So at the end of the day, you're just boiling down to these smart assistants. They're just fancy microphones and speakers in this architecture, with the real AI happening up in the cloud. But it's not just a pure AI play. There's some normal programming in here as well. We're just doing the interfacing using natural language processing. Economics. This graph's slightly we can use AI as pattern recognizers. Neural networks are very good at recognizing patterns, as are humans, I mean. So lots of people have tried to use it in economic forecasting because the theory is that there is a pattern to it. We're just not great at spotting it. Neural networks are great at spotting patterns that we can't, as good as we are at spotting patterns, sometimes neural networks can pick up on patterns we haven't recognized. So lots of people are doing algorithmic trading using neural networks to try and do some predictive of where is these markets going to go, where is all these graphs going. The neural network I showed you isn't great at this, what we call time series. It's not great at, because there is AI field that can handle this, but the basic one I showed you can't really handle with what we call history. So time series, you have to use very fanciful AI mechanisms, but we won't go into those today. But these require memory, and that's a whole different architecture. There's some more programming slides about economics. Automation is another good one. I like automation, well, this one, because this isn't the first, I'm sure we're all aware this isn't the first time automation has put jobs at risk. I mean, we had the printing press back in the day, horse and carriage, so this isn't the first time running. But what's interesting, it's the first time that white-collar jobs are at risk. So all of a sudden, I'm getting lots of contact from lawyers, from accountants, are really worried about how their job's going to look in 5-10 years' time, because it's the first time that it's not been blue-collar jobs only that's been risked from automation. The truth is that it's going to help jobs. Rather than being if you're a lawyer, for instance, it's going to take away the mundane, the boring jobs, the easy ones to deal with. Such things, or from an employment perspective, like, can I sack an employee? Question back is, have they been there less than 2 years? Answer, yes, you can, unfortunately. That's a different thing. So I'll handle all these boring, mundane, very obvious question and answers scenarios. But what it won't do, and for foreseeable future, is the real strategic parts that lawyers do, the real complicated cases, the real nitty-gritty ones. So I think the only risk what I can see that comes from this is, unfortunately, all the boring jobs tend to get done by the grads, or the people just coming, the new lawyers that are supposed to deal with this and get into their jobs. They're now the ones that are competing with AI. How are we going to get this natural progression from university into the professional job if the entry-level jobs are being done by AI? We can go on to this. The other one is the car industry. So AI has enabled the car industry. We heard someone we heard the keynote rubbishing the trolley problem and saying that it's never going to happen. Unfortunately, as the car industry, it does actually have to think about that scenario, because they'll get very harsh questions from their insurers and from the government if that scenario, as unlikely as it is to happen, does happen. So introduces a new whole moral dilemma to the AI perspective. The other one is this one. And I could go into drones doing deliveries and that kind of thing, but I think what's interesting is, well, what happens if, for instance, I was recently at a major port in Britain, and at any given moment, that port has 60,000 cars. And if you take it to the next stage, you think 30 years down years, that's 60,000 autonomous cars on a port moving around. And the port is responsible for the safety for that area. How are they going to keep hold of the situation and make sure they're maintaining safety over all these new assets? And we're going to employ people to do that. So AI is going to have to play a role, and also it's going to be watching itself in a sense. We're going to have to employ AI systems in this port to keep around all these moving assets, and that's just on a port. If we then scale it up to a city in terms of autonomous cars, in terms of drones flying around doing deliveries, how many moving things are we talking about all of a sudden? A lot. And that's not going to be a job for a human to watch over all them. So AI is going to create a lot of jobs for itself as well, because of the sheer scale of the assets moving around. And that's a bit of white-collar jobs mentioned earlier. And I put this one in because we've talked a lot about machine learning. All the neural networks, that's a great machine learning. The machine's learning how to do its job. But that's not all what AI does. We mentioned earlier evolutionary computation. And if I mentioned that neural networks was taking inspiration on how the brain works, what we're going to briefly touch on here is genetic algorithms. So we can say what genetic algorithm, this is a slide, this is a mathematical problem, the traveling salesman problem, and ways to solve it. I'll place in the background. The premise being is the traveling salesman problem is a good mathematical problem, and finding the optimal route to visit all these dots and minimize the distance that you travel to do so. Genetic algorithms are really good at this, but genetic algorithms, they're more inspired by natural selection. How does biology improve itself on a generational perspective? This is just a random guess one. With genetic algorithms, what that's doing is it's replicating DNA and how parents pass their attributes on to their child. And then we try to do this with tech systems as well. How can we take the attributes of a good tech system and try and improve that from an evolutionary perspective? And we can start to see a better fit solution here. This goes on for a while. A good example of this is if we think about designing electric generating windmill, because there's a lot of parameters involved here. What's the optimal height to have this windmill? What's the optimal length to have the blades? What angle should the blades be? All these kind of questions. With each parameter you add, the number of permutations exponentially goes up. So what we can use for genetic algorithms is we have what we call them populations. So you'd give an attribute of the height, you'd give an attribute of the blades, you'd give an attribute of the angle of the blades. You then calculate, we'd randomly give the values that you think might be true. You then evaluate those values, and you get a fitness test. But you do this over say a population of 100. So you do this 100 times. Then you could, for example, then take the top 10% and then mix the attributes together for the next generation and do that across the whole population. So hopefully at the end of it, you'll end up with a good solution. It works quite well. I really like genetic algorithms. As I promised, it was quite a short one. So